Hello. So, welcome to the fourth live session of the NPTEL course Design of Reinforced Concrete Structures. I am Sanjay Kumawat, and today in this live session, we will be having a total of again three questions. And out of these three questions, one questions will be of finding ultimate moment of resistance of doubly reinforced concrete beam, and two questions will be on design of singly reinforced beam, and the third one will be on doubly reinforced beam. So let's see them all one by one. Coming to the doubly reinforced beam, first let's look at the concept of doubly reinforced beam. How the stress profile and the stress strain profile of this doubly reinforced beam looks like. So if I talk about this doubly reinforced beam, the strain profile as well as the stress profile they remains same as that in the case of singly reinforced beam, because the strain profile as well as the stress profile they depend upon the type of material used. So whether it is doubly reinforced or singly reinforced, the type of material we are using here is concrete and steel, and the maximum ultimate strain in the compressive part, that is for concrete, we are assuming it to be 0.0035, whereas for steel in the tensile part we are assuming it to be greater than 0.87 fy by e plus 0.002. Now coming to the stress block, the stress block is a parabolic type. I had explained you this in the previous live section that this stress block, it has come from the stress strain curve of concrete. So when we divide the stress strain curve of concrete by 1.5, firstly we take 0.67 times of fck, then divide it by 1.5 to get this 0.45 fck, and this 0.45 fck is the design characteristic strength of concrete, and it varies linearly up to a strain of 0.002, not linearly but it varies from 0 to a value of 0.45 ck up to 0.002 strain. Thereafter it remains constant for the strain of 0.0035. So the only difference which comes up for doubly reinforced beam is that, let me explain you here. You have already let me switch on my pen first. Okay, see. So this you are already familiar with. Now in doubly reinforced beam, what's the difference? Firstly, let me tell you why we go for this for a doubly reinforced beam. That is why we have steel on both tension as well as on compression side, as you can see it here. These are the tensile steel and this is the compression steel. So why do we go for providing steel on both the side of this concrete? So there are various reasons and you must all be known about this. That is, the first reason being that there can be load reversal. That is, the load reversal is we are assuming that the load will always come from the upward side and the beam will always bend up like this, but it is not that important. Sometimes there can be load reversal and the beam can bend in the opposite direction also. This load reversal can occur due to varieties of things, such as it can occur because of earthquake loads are back and forth load. So because of this back and forth we can have tension also on the upper part of the beam, apart from the downside part. And also we need doubly reinforced beam when the width of the beam is restricted. That is, if this is D and this is B, and the architects wants us, sorry, this is B, and the architects wants that this beam should be of this particular size only, but the load which is coming on this beam, it is demanding to be of higher capacity. So for higher capacity, since we cannot increase this D, what we will be doing, we will be providing extra reinforcement in the compression part. So this was the reason why we are going for doubly reinforced design of beam. So let me explain you first the how the forces are being calculated in doubly reinforced beam. So this is very similar. Firstly, see, this is the cross section. In cross section, you are already aware of bars in the tensile zone, while now we also have bar in the compression zone. Let us assume those bars are three bars in compression zone. These are ASC, while this is AST. Okay. Now conceptually speaking, what we always do is we go for force equilibrium. So force equilibrium, what we always do, we assume that whatever force, compression force is in concrete, that compression force, it is balanced up by the tensile force in steel. But what about this steel in the compression part now? So this compression, it is for sure that this steel will be in compression when the load is acting from above. Okay, so because of this extra force which is coming from the top, now we will be having a compression forces in these top bars, and this compression force in the top bars has to be balanced by extra tensile force which is to be provided at this level, at the tensile force level. So now what can I say, okay, let me firstly erase this and explain you more clearly what I am trying to say. See, now I have my doubly reinforced beam like this. Suppose there are four bars here, and also we have four bars here also. Now I can divide this beam in this manner. Okay, so plus plus what, plus what, now this four bars plus, let it be, this be five. Okay, two. So now this will be ast1. Ast1 will be taking care of the compressive forces which is coming up from the concrete. This is ast2. AST2 will be taking care of the forces which is compressive forces which is coming up from the coming up from the tensile steel present in the compression zone. So this is the way we are classifying it, and based upon this you can easily understand this resultant force diagram. So let's look at it. Now the total tensile force, you can see it here, the total tensile force you can also write it in this manner: ast1 plus ast2. Okay, so AST1 will be balancing CUS, whereas AST2 will be balancing CUC. So CUC, you already know how it came. It is the net compressive force which is taken up by the concrete. Now what about CUS? CUS, how it is coming? CUS, it is easy. We know how to calculate the forces in bar. Stress in the steel which is present in the compression region into area of that steel. So this is the total force present in that bar. Now what is this? How do we come up with this value? Minus 0.45 fck into asa. So when you solve this you will be exactly getting this. Let me explain you how we are writing this minus 0.45 fck. So cuc you can see it here, it is 0.36 fck b into xu. Now this is the compressive force in this. Let me erase this. So CUC is the compressive force in this part of the concrete. But now I am replacing a small diameter of this concrete with this 2 bar. What can I say? I am removing a force which is of area ASC and which is of stress 0.45 FCK. So I am removing this stress and I am replacing this stress by the stress in the steel. That's why I will have to remove this 0.45 FCK. I hope this was clear to you. So this was about the stress profile and the strain profile of doubly reinforced beam.
Sir,
And
can we just subtract the 0.45 FCK ASC value from the stress block of the concrete,
yeah, you can do that.
and it will reduce certain area and we'll get CUC value with 0.36 will be something
See,
somewhat different.
Shivam, the problem is you can do that, but that would be true only for the forces. But when you take the moments, moment will be the distance of this 0.45 FCK will be the distance of AS into AFS. Did you get me what I'm saying?
Yes,
We
yes, sir.
uh,
I also thought about that. So the reduction in the area from the where the steel bars are there. So the movement has to be taken from that point only. You know?
yeah, yeah. So that is the reason we are subtracting it from CUS and not from CUC.
Okay,
For force equilibrium, you can do it either way. It won't matter. But for moment equilibrium, it would be a problem. Okay.
okay.
Okay. Then now you are now very familiar with the resultant forces in a doubly reinforced beam. Now this is the force equilibrium, and this is the moment. You can easily like figure it out. Cu into d minus 0.42 and cus into d minus d dash. D dash is what is d dash? It is the effective cover from the top for the top compressive reinforcement. So now let's look at one problem. So what the first problem of today's class says, a doubly reinforced beam has the section properties as shown below. Okay. Assuming M20 concrete and Fe250 steel, calculate the moment of resistance. What is the ultimate moment of resistance? Okay. So now it is asking us to find ultimate moment of resistance. So similar steps which we followed up for the calculation of ultimate moment of resistance for singly reinforced beam. So what were all those steps? What we need to first do? We need to first find whether this section is over reinforced or under reinforced. Why we need to do that? Because if the section is under reinforced, then only we can use the stress in the steel as the yield stress. But when the section is over reinforced, the stress in the steel is not the yield stress, but it is a value which is less than the yield stress. I hope you remember the graph which I explained many time in the previous lectures. There is a linear zone and constant. So what was I saying? If the if the beam is under reinforced, then only we can take the yield value of steel as 87 Fy. But if it is over reinforced, we need to take some other value. Okay. Now before going to this problem, let me also explain you, or you all must be familiar with this. See, you all must be knowing we okay, sorry. You all must be already knowing this. This is for Fe250. So Fe250 does not have any proof stress. While when I draw it for Fe415 or uh, Fe500, okay. So when I draw it for Fe500, there is a proof stress of 0.02. Well, there is no nonlinear zone in this Fe250. So I think in lower classes you must have studied this. So you should remember this year as well. So as soon as I left the or as soon as I leave the linear zone in Fe250, I enter into the plastic zone. So this is the elastoplastic region of Fe250. This is a bilinear curve. Well, this is also a bilinear curve, but we have a small amount of non-linearity here, because of which there is a proof strain of 0.002. So why did I explain you this here? Because in our question we don't have Fe415, now we have Fe250. And what we need to do, firstly we need to find whether our section is over reinforced or it is under reinforced. So these are all the given data. The width of the beam is 300 and 600 is the depth, overall depth, while effective is 550. And the cover, it is mentioned it has 50, the cover at the top. And what we have, grade of concrete, we have grade of steel, and here I have calculated it for you, the area of tensile steel and the area of the compressive steel. Okay, now let's look at the problem. How do we initiate? See what I am doing. Firstly, I am using the stress force equilibrium. The force equilibrium, there are two compressive forces. While I already told you, you can divide it as fst into ast1 plus ast2, but you don't need to do that because here the classification won't matter. Okay, so first assumption is we are assuming that the FST is 0.87 Fy and FSC. This assumption we also did in singly reinforced beam, but I didn't mention it over there, but I'm now mentioning it over here. Like we are assuming 0.87 Fy as the yield stress in both the steels. Which are the two steels? The one in the tension zone and the other in the compression zone. Both have the 0.87 Fy. So what does that mean? What I'm assuming? I'm assuming that my strain in the concrete is greater than 0.002. That is the inelastic strain. Okay, so now what I have done, I have equated cuc plus cus equal to tu and found the actual depth of neutral axis. And with the assumption of this, I get the actual depth of neutral axis as 212.7 mm. Now for 250 steel, we know the limiting depth of neutral axis 0.5 0.53d. This I have shown you in previous classes, and if you don't remember 0.53d, you can easily use the stress block diagram. 0.0035. This is what XU limit. This is what this is 0.87 Fy by E plus 0.002. Sorry. Okay, so this is D minus XU. So you can also calculate this 0.53 from here. So now we can see what we can see. The limiting depth of neutral axis or the maximum depth of neutral axis is greater than our actual depth of neutral axis. What does that mean? Actual depth of neutral axis is greater. So I told you we are always taking the strain in the concrete as 0.0035, and now since XU is greater, XU max is greater and our XU is smaller, so it will be something like this. So this is under reinforced section because the strain in the steel is more than the ultimate limit strain in the concrete or the crushing strain in the concrete. So this is over reinforced. So whatever assumption we took previously 0.87 Fi, that is true for the steel which is present in tensile zone. Now let's see what we have for the. So with this assumption we got that the steel in the tensile zone have a compressive stress of 0.87 Fy. Okay. Now what about the steel which is present in the compression zone? Now the steel which is present in the compression zone, you can see this is 0.0035, and the steel, if you draw the cross section, it is present somewhere here. Okay, somewhere we will be having here 0.002 or some other value. So we need to verify whether the strain in the concrete has exceeded this value. So how we will be doing it? Firstly, we have assumed that our strain in the concrete, our stress in the concrete is 0.87 Fy by Es. So I have this value now. Now what will I do? I will use again the compatibility. How will I use it? This is XU. Okay, no need of this. Okay, let me redraw it properly. Okay, so this is 0.0035 for a distance of XU. Now at some point we have here bars. Which bars? The compressive bars. So this is 0.0035 and this is strain in those bars, which is epsilon cs. So I can calculate it from here. Epsilon cs divided by xu minus d dash, that is equal to 0.0035 divided by xu. So from here what you can calculate, xu know it already. I can calculate the strain in the compressive bars. So what strain I get? I get the strain of 0.00318. So this 0.001 00318, it is greater than this value. So what does that mean? Can anyone of you tell me? I have assumed the stress in the compressive bar has this, and for that stress I am getting this strain. But the actual strain in our bar is this, which is greater than this value. So what does that mean?
Uh, the compression zone is yielding.
Yeah, see, what does that mean? Let me explain you again. I have considered that our bar is at this point. Suppose this strain was 0.001, but now what I got my actual strain has 0.00318. So it doesn't matter because for this part we have the stress as constant. But if for example our actual strain would have come up somewhere here, then it would have mattered. Okay. So for the time being, the problem is easy. So you can see whatever we have assumed, we have validated it here. So we can use for both the steels, we can use this as the yielding stress. Okay, fine. So now we can calculate the ultimate moment of resistance. So this is the value which is coming. So this was about the first problem, and a problem can be also of the type over reinforced, but I have not included it here. In the previous class I also took a problem on over reinforced section, So similarly, you can also have over reinforced section for doubly reinforced beam. Only thing you have to do is, now this stress value won't be equal to 0.87 fy, but from that table, the table which includes inelastic strain and elastic strain, by using linear interpolation you will have to calculate the actual stress in the steel, and then you will have to put it over here. That is, you cannot put 0.87 fy, but you will have to put some other value. Okay, fine. Now let's move on to the second problem. I wanted to cover all types of problems. So since there is time limitations, I am just explaining you orally. But in previous classes, I also did over enforced problems. So I don't think that would be an issue. You can follow it up from any book. If there is any doubt, you can ask me. So what does okay? So what does the second problem says? A rectangular reinforced concrete beam located inside a building in a coastal area is simply supported on two masonry walls which are of thickness 230 and they are placed 6 meter apart center to center. Okay, so we have a beam. They are resting on a 230 thick walls which are placed 6 meter apart. Now the beam has to carry a distributed live load of 10 kilonewton per meter and a dead load of 5 kilonewton per meter in addition to its own weight. Okay, so its own weight will be a dead load and 5 kilonewton will be the other dead load, and we have a live load of 10 kilonewton per meter. Now design the beam section for maximum moment at midspan. Assume Fe415 steel and 8 diameter stirrups. So these are all the given data. Okay, sorry, the given data is not there. I just broke up the suspense. So can you all tell me what data is missing up in our question? We have Fe415 steel and all other dead load and live load are also mentioned. Can any one of you tell me what data is missing in our question? They have only mentioned me that the building is lying in the coastal area, in the coastal town.
The grade of concrete.
Okay, so the grade of concrete is missing. So the grade of concrete based upon uh, the region where the building is lying, we can see the grade of concrete from IS 456 2000. So let's see how we can do that. So the table 3 which shows us the environmental exposure conditions. Here here we can see that the coastal area region lies into an environment of moderately exposed region. So this moderately exposed region, the table 16 says that for moderately exposed region we need to use a minimum grade of concrete which is M25 and a nominal cover of 30. So now we have the grade of concrete, the grade of steel, and all other data we need to solve this problem. What we need to do, firstly, let me also explain you what does design and analysis means. Design, it means we have some load, and for that load we need to decide the dimension of the beam and the amount of reinforcement which which the beam would be carrying to safely take this bending moment which is coming because of this load. So this is about design. And what is analysis? Analysis is, we already have a beam. What forces that beam is taking, what moment that beam can take, what is the maximum shear force and bending moment the beam can take, that is nothing but the analysis of that beam. While design is, we have the forces, we need to design the dimensions and the reinforcement. I hope that is clear. Okay, so we have grade of concrete. Now let's assume a trial section. I have assumed a width of 250 and let's assume the depth of the beam has the total span divided by 10. Just a second. So our total span center to center it is 600. Sorry, 6 meters, so 6000. So I am approximately taking my overall depth as, like, the length would be 10 times the overall depth. So the depth will be 600 and I am taking a trial width of b equal to 250. Fine. So for this effective depth, now let's calculate the uh, design moment that this beam can take with these dimensions. So for to calculate the design moment, okay, what is design moment? Design moment means what all are the moments for which I have to design our beam. So those moment will be coming up from the dead load and the live load. So to calculate moment, you all must be familiar how to calculate a moment. For moment, I would be needing the length of this beam. So the center to center length it is given as 6 meter, but IS 456 2000 what does it says? the length of the beam, it should be taken as minimum of the center to center distance, or it should be taken as the center to center distance minus the width of the support, which is 230, plus the depth 550. So I have already calculated it, and the minimum value from both of this is 6 meter. So this was the effective span. Now what we have, we already know the dead load would be the self weight of the beam. So the unit weight of the concrete is 25 kilonewton per meter cube. I have multiplied it with the assumed trial depth and width of the beam. I got this as the distributed load due to its self weight. Now what I have a dead load of 5 kilonewton per meter, which is already mentioned up in the question. So what can I do to find the total dead load? I am now adding up 3 plus 5. I got this as the dead load. Now let's look at the live load. Okay, so live load, it has been already given as in the question. What was the live load? Live load was of 10. Okay, so now factored load would be, I had explained you this, we have only dead load and live load, so the factored load will be 1.5 times these values. So I am getting this as the factored load. So this is, since this is a simply supported beam, and for a simply supported beam, when it is acted upon by a UDL, the maximum bending moment will be at center, which will be of magnitude WL square by 8, 126 kilonewton per meter. So this is the moment for which I have to design this beam, or the beam should take up this moment. So I have already decided the breadth and the width, sorry, the depth and the width. Now what I need to do, I need to calculate the area of steel. So how can we do that? What we have is the formula which we have with us is the limiting depth, limiting moment carrying capacity of beam. So don't just get scared with this what I have written up here. You are very familiar with this formula, 0.36 fck b into xu into d minus 0.42 xu. Okay, so what you can do, you just put xu equal to xu limit. Okay, so what is xu limit for fe415? It is 0.48 d. Fine. So you can put up xu, you have b, you have fck. What you will be getting, you will be getting the limiting depth of neutral axis. So you can calculate the d from here. The only unknown, what we are trying to do here is we are finding what is the minimum depth which is required to take up this moment. You are getting me what I said? We have fck, we have b, we have xu, limiting xu, m. M we are not taking as the limiting, but yeah, we are using the formula of limiting moment carrying capacity, and we will be putting up this value, and I will get d. So sorry, I will get d. So this is the minimum depth which is required to take up this moment, okay, for this grade of concrete, and XU has the limiting depth. So 382 is the value. So at least 382 depth has to be provided in order to take a moment of 126 kilonewton per, not per, kilonewton meter. So what dimension I have assumed? I have assumed a dimension of 600 So that is very like not economic design that would be. So I will have to reduce that D. So let's take some other value of D. Now I am assuming that D has 450 and the let's calculate the effective depth. What is this nominal cover? Nominal cover has to be 30. Stirrup it is given as 8, and let's assume the tensile steel with to be of 25 dia. So by using this, what I will be getting, I hope you are clear with this. This has been already covered up in the lectures. So d effective depth I am getting it as 400 So just remember the steps. What firstly we assumed a trial. For that trial, I have calculated the mu. Mu is the moment for which I have to design the beam. Then once I get that moment, for that moment, I will be calculating what is the limiting or what is the minimum depth of beam which is required for that moment. And then I will be assuming based upon my calculation the the depth which would be economical, and then I had calculated the effective depth. Okay, now let's move on further. So we have the dimensions of the beam. Now what further is needed? We needed the area of steel. So area of steel can also be calculated. How it can be calculated? Again, don't get scared with these formulas, but I think these formulas you can derive it very easily. Sorry, m is equal to 0.87 fy ast d minus 0.42 xu. Now what you have to do to convert this area into percentage, just divide this by bd. Here also you will have to divide this by bd. Okay, so when you just rearrange and recalculate it, you will get this formula. So you have fy, you have fck, you have moment. So now you can easily calculate the percentage of steel which is required. Or there is no need to calculate the percentage of steel, just directly calculate the area of bar from this formula. And from that area of bar, since we have assumed the uh, diameter of bars in the tensile zone as 25 mm, we can calculate the number of bars. So this is the area of steel. I am assuming 3 bars in one layer. So the diameter would be, the required diameter would be 21.2 mm. Now diameter which I assumed was 25 mm, that's fine. That's why I will be modifying this and providing one bar of 25 mm and two bars of 20 mm. So the AST which is provided over here is, the AST provided is this, AST required is this. Okay, so AST provided is greater than AST required. So that's fine. If we are providing more steel than the required, then it is good, but less steel would not be good. Okay, so the percentage of steel which is provided is 1.21, which is less than the limiting percentage of steel. So how to calculate limiting percentage of steel? So you already know for from force equilibrium what we have, 0.36 fck b into xu, that is equal to 0.87 fy ast. Okay, now if I take xu equal to xu limit, then I will get ast equal to ast limit. So you can just rearrange this and find it very easily. Fck b into xu limit, that would be equal to 0.87 fy ast limit. Just divide this by bd. So here also we will be having to divide it by bd. Now what will be this term? This term will be 0.87 fy percentage limit. So this is the limiting percentage of steel, and you can calculate limiting percentage of steel. So that limiting percentage of steel would be is greater than this value, so that's good to go. Now we have completed the design of singly reinforced beam for the given loading. We have the breadth and the depth. We have the area of steel. Now we need to do some additional checks on our beam to ensure further serviceability or further safety of our beam. So let before going to the check, let me first explain you the various checks or the concepts behind with this check. So the first one being the deflection control. So IS 456-2000, it ensures the deflection control by this ratio. It always gives some proportional formula. I have mentioned it here, no need to write. So this is the deflection of the beam, this is length of the beam, and this is the depth of the beam. So IS 456, it always specify the deflection criteria in this format. So why does it specify in this format? I will be explaining you it here. So you can see. Okay, so you all know maximum mid-span deflection of simply supported beam. When there is a simply supported beam subjected to UDL, okay, so what is the deflection at the center? So the deflection at the center is this. You all have studied this in lower classes. So I will now break up this deflection into this manner. Now let's further look what will be happening. You all know this, from where the from where does this come? Can any one of you explain? What is this?
This is section modulus into the stress gives the moment.
Yeah, you all must have remembered this formula. Sorry. You know what is this? You This is flexural formula, and the way I have remembered it is very funny, but the important thing is you should remember it and not how you are remembering it. So I have remembered it in this fashion. Elizabeth Rani, may I follow you? Did you get me? Elizabeth Rani, may I follow you? Okay. So from here, this F is nothing but sigma into Z. Z is what? I by I. So this is the way I have calculated it here. So why I am showing you this? Now you know, for a beam, I by Z is d by 2. Okay, for a beam of depth d and width b. So this d by 2 for a rectangular beam. And now our deflection I have replaced. You can just simply figure it out. I have replaced something here. WL square by 8 is what? Maximum moment of this beam, simply supported beam. WL square by 8. So I have replaced it with M max. L square by, and rest of all are the same. Now I am replacing this M max with this. So I am getting sigma this. Let me just delete this. Okay, so now I am getting this relation. Now for a particular cross section of a beam, the permissible stresses in the beam, it will be remaining constant for a beam which is of constant area, or what can I say, constant cross section and and similar material. So I can take sigma permissible by ei has a constant c, because those will be constant for a particular beam of a similar material and similar width. Now what we have is L square by I by Z. Now you see what I have done. Now C equal to L square I by Z for rectangular beam. I have replaced it with this. So now I have this relation. Further what can I do? C is a constant, 2 is a constant. So I am replacing them by K. So now you can see that is the reason why code specifies the deflection control of beams by this relation. That is the deflection into our beam or slab that is proportional to the 1 by d. Okay, ll you can cancel, but that is fine, don't cancel it. So the deflection is always specified in this format. So why this format? This format, it comes up nothing from this all formulas. Okay, is that fine? So now let's see. This was just to make you familiar with L by T and delta by L. So now L by D for prismatic beam. What is prismatic beam? Prismatic beam is nothing but a beam of uniform length or cross section. So for prismatic rectangular beam and slabs of thickness up to length, L by D maximum, L by D max. So this is nothing but, delta by L, it is proportional to that. So it should have L by D basic into KT into KC. So what is KC? KT and KC are nothing but modification back factors based upon the percentage of steel in tensile zone and in compression zone. And L by D basic, it has been specified by the code for different types of beam. So L by D for cantilever beam is 7, L by D basic for simply supported is 20, and 26 for continuous span. And from where does we get this modification factor? So just remember, L by D ratio, it should not exceed this value, L by D basic into KT into KC. Okay, KTR. Okay, this also has many concepts. KT is what? Modification factor for steel which is provided for the provided to resist the tensile force, whereas Kc is what? Kc is the modification factor which is provided based upon the percentage of compression reinforcement. Okay, so the physical interpretation of this is, why do we need to multiply by this modification factor, is that by from researchers, from many researchers, it has been observed that the bars which are present, suppose this is the longitudinal view of our beam. So this is the tensile steel, this is the compression steel, and this is the tensile steel. So it has been observed that the compression steel, they are actually responsible for reduction in our deflection, whereas the compression steel are responsible for reduction in the deflection, while tensile steel are responsible for increase in the deflection. Okay. And uh, and the most importantly, you should be knowing that the stress which we are taking during the calculation of deflection control of beams, that stress is not equal to the yield stress, because the deflection checks, we are calculating it based upon the working stress method. So a simplified formula to calculate the stresses by working stress method has been given up by IS code. So this is the stresses into those steel. Okay. So how to do this? Let's see for our problem 2. So these are the design checks. Firstly, we need to check the flexural strength for the percentage of steel which is provided. So this is nothing but 0.87 Fy AST into 1 D minus 0.42 FCK, a modified version of that formula. So this is the, for the provided amount of steel, this is the moment which it can resist, and that moment it is greater than the moment which is coming up from the load. So that check is successful. Now the other check is deflection control check. So I have already told you the stress in the steel you need to calculate based upon the working stress method. So to calculate it, the a formula in a simplified formula in IS code has been given. So just put up the area required and the area provided from the previous slides. I have kept it up here for you. You just substitute it here and you can get this. And now you know that L by D max, it should be equal to this value. Now let's see. Okay. So KT is coming out to be 1, and KC is also coming out to be 1, based upon the FS and percentage of steel. So now you can see, will we be having KC in this case? Can anyone of you tell me what is KC? KC is modification factor for compression steel.
Compression. Compression.
So we don't have compression steel in this problem, so it is assumed as 1. There is no compression steel, but KT you can just see it from this graph. Again, remember why we are using KT and KC, because it has been found that the presence of the steel, it affects the deflection, and it is a common sense thing. Presence of the bars would definitely affect, but how it will affect? The compression bars will limit the deflection, whereas the tensile bars are found to be increasing the deflection. So based upon that, this should be our LD max, and based upon the dimensions of our beam, I am getting the LD max as this, so which is less than this value. So our beam has passed this check also. So this was all about the design of singly reinforced beam. Now let's quickly jump on to the design of doubly reinforced beam. So this is the third problem. A rectangular reinforced concrete beam. Just a second, guys. Okay, sorry for the interruption. A rectangular reinforced concrete beam located inside a building in a coastal town. Again, the coastal town, the thing you know, M25, is simply supported on two masonry. So this is the similar problem. The beam has to carry a distributed live load of 10, a dead load of 5. Now the only difference in this problem and the previous problem is we now have a concentrated mid-span dead load. This is the extra dead load which is acting. Okay. In addition to its own weight, the size of the beam is limited to 250 mm by 400 mm. Oh, so there is a twist now. Just use your common sense and tell me. In the last problem, there is no need to lie. You have to solve this, but just use your common sense. Common sense. Last in the last problem, we had a live load of 10, we had a dead load of 5, and we had a dead load which is equal to self weight of that beam, and that beam was of 250 by 450. Okay. Now in this case, we have a dead load of 10, sorry, live load of 10, a dead load of 5, a concentrated dead load of 30, and now the self weight of beam, which is having a restricted cross section of 250 by 400. Can you just see? Now the load has increased, but the cross section is reduced. What does that mean? It simply means now we there can be chances like we will have to design doubly reinforced beam. Because why I am saying you, because d minimum which we got from that problem was around, can anyone of you remember? D minimum from that problem was around, I think, 350 or 399, something like that. So this we designed it for this load, but now we have some extra load and the cross section is also reduced. So by comparing these two problems, I am pretty much sure that we will be having to design a doubly reinforced beam. Don't worry, this I am only trying to visualize you, but there are like specific methods you will be able to know by calculation itself, like this beam has to be designed as doubly, it cannot be designed as singly. How to do that I will be showing you just in further slides. So these are the given data. So live load, dead load, central load. This is FE and FCK is also given. Okay. This is stirrup. Okay. And B and D are also given. So they have already fixed up the dimensions, but now I have to find the area of steel which is required. So let's see. So again, similar steps. Effective span length is D. We already know. Now I'm taking the effective cover as 50, so 350 mm. So now again I am getting the span length as 6 meter. Now let's calculate the load in the similar fashion. You can see the dead load of the beam, which is added up with the dead load which is acting on it, that is 5. So 5 plus 2.5, 7.5. Then I am adding up the dead load and the live load with a factor of 1.5, and now I'm getting this the final UDL load. Now, apart from this, I also have a dead load which is a point load, 30 I think. I need to multiply it by 1.5. So it will also become factored. Cross section of this beam is 250 by 400 mm. Okay. So, okay, you can see it here. The factored load, point load. Now you know this will be WL square by 8 and the other one will be WL by 4. By we can use the principle of superposition here. Okay, so this is the final moment for which I have to design my beam. So we already have the dimensions. I know I know my simply supported beam can take a maximum moment which is equal to mu limit. So let's look. I know Fe415 and M25. So you can substitute that. You know, I think you know from where this came. This came from 0.36 FCK B into XU D minus 0.42 XU. So when you substitute XU equal to, what you have to substitute, XU equal to for Fe415 0.48D. So when you substitute this in this problem, sorry, in this equation, you will get this. So that would be limiting moment of resistance for this beam. So that is coming out to be 106. But the maximum moment for which we have to design this beam is 186. But the maximum moment this beam can take is 106. What does that mean? 186 and 106. This is the moment for which I have to design the beam, and this is the limiting moment of resistance. So this is the extra moment for which I need to provide compression steel in my beam. Okay. So you can see it here. Since my moment which the for which the beam has to be designed, it is greater than the limiting depth of neutral axis, we need to go for doubly reinforced beam. But we already knew it from comparison from the previous problem. So now you can calculate the area of steel. From area of steel, how you will calculate p limiting. P limit I explained you just now in the previous slide. So you calculate the p limit. Now this is the area of steel which you need to provide in tension zone. So this is AST1, okay, which will be taking care of the compression in the concrete. Now we are assuming the, what is this, we are assuming the diameter of this compression reinforcement as 20 mm. Why we are assuming it? Because we need to calculate the d dash. D dash is nothing but this. So clear cover plus the stirrups, which is 8 mm. This is 30, this is 8, and this is 20. We are assuming it. So we got d dash as 48. Okay, so why we are calculating this d dash, I will be explaining you. Okay. Okay, so from this percentage of steel, I can calculate the area of the steel, or you can directly calculate the area of steel that I explained you just now. So from this area of steel, you can calculate the number of bars which is required. So we got, sorry, we got AST1. Now it's time to calculate AST2. This is just a diagram for a reference, and this AST2 compression will be ASC. Okay. Okay, so for this difference, now I am calculating the AST2. So it is 734. So now you can see the AST required will be AST1 plus AST2. So this is the total tensile steel which I have to provide. Now I am assuming 3 bars of 28 phi. So AST provided is this, while AST required is this. This is similar to the one which I did in the previous second problem. Now calculate actual D. Why actual D I am calculating? I am calculating actual D based upon the D which I am using up here, 28. Because the D which I used previously was, what was it? It was 350. Sorry, not phi, na. What was the phi value? See, so based upon this, I am calculating now our actual depth as 348. While what I had assumed 50 has the effective cover previously, but now when I'm assuming 28 mm bar, so the D which is I'm getting is 348. So this is less than this, so I need to revise my whole calculation based upon this D value. What all this whole calculation is, I need to again calculate the limiting moment of resistance. So I now have D. This is the limiting moment. Now again the area AST1, then again AST2. Again I am adding up them. So 173, which is, this is the AST required, which is less than the AST provided. So it is good. So now what I am doing up here is, what I am doing this, I am calculating the, what I am doing up here. Anyone?
AST2, AST2 calculation.
AST2 calculation. Yes. So this is what I'm, the total required minus the what I have provided up here, the limiting one. So this is I am getting AST2. So this AST2 tensile force will be balanced by compressive force, by the compressive bars. Sorry. This is not very tough problem. Just revise it after the lecture. You will be able to understand. So now I need to calculate the ASC. So for ASC, I need to have D dash. So based upon D dash by D ratio, I can get the stress in this bar. FSC I can get from interpolation. So why I am using this interpolation method? Because for compressive bars they are having a different strain than the strain which is present in the this bars, tensile bars. So I can calculate the stress in this compressive bars from this interpolation. This table you can get it from IS 456. Now I am getting the stresses as this value 344.7. Strain you can calculate from the strain diagram. So based upon that strain, you can calculate this. Now what do we have? We have a stress of this value in the in the steel, in the compressive steel. So based upon that stress, now I am calculating the area of steel required, and area of steel required you can see up here. It is coming out to be 869. So again I am assuming some bars 25, and then I am calculating the percentage of steel in tensile and in the compression zone. Then I have to give the checks. This check I want you to do it by yourself. Just figure it out how I am doing up this. It is not very difficult. You can do it by your own. And the last one is the deflection control check. This is also similar to what we did. Only thing which will be varying is now we have KT also and KC also. Okay, so this was all about this problem also. So if you have any problem, you can come up with that in the next lecture. So for today, I would be liking to conclude this live section here only. Today we took two design problems and one problem on calculation of ultimate moment of resistance of doubly reinforced bar. Okay. So if you all have any doubt, you can just ask me, or else I would be concluding this class. Anyone of you? Mithilesh, you are not audible. No, no. You are not audible, Mithilesh. Can you type your query in the chat box if it is possible? Yeah, you can use a Subramanyam book and Krishna Pillai. Those two books are good one. For concepts, you can for problems you just see the Krishna Pillai book, Krishna Menon, and for concepts you can refer the Subramanyam book. It is good one. Any other questions?
Sir, I want to ask, in the previous lecture, in the previous session, you just calculated the AST for the that over reinforced section.
Yes.
Uh, uh,
No,
Let
no.
me open my notebook.
Did I do the AST calculation?
The FY value, sir,
Okay.
means whatever be the stress in the bars in the over reinforced section. I think so that
Yeah,
is
yeah.
being fine. So we have the assumption that, let me open my notebook first.
Okay. You want to share it?
Yes, sir. I want to say something about that. So we have the assumption the maximum strain in the concrete at outermost compression fiber as 0.0035,
Yeah.
and the maximum strain in tension reinforcement as 0.002 plus 0.87 Fi upon yes. So, sir, if we have a neutral axis which is less than the limiting depth, then we can have uh, a strain in the concrete as less than 0.0035, and on the in the reinforcement we can have the stress the strain as 0.87 F5 and upon ES plus 0.002. uh, are you getting what I'm trying to say?
Yeah.
And it can be said in another way also. Uh,
You are saying if the you are saying why we can exit this value, you are saying.
uh, I'm trying to say that if the compression steel at the top fiber is less than 0.0035 and tensile strain at the steel is that value 0.002 plus 0.87, that value,
Okay.
so the assumption is satisfied. And we can have a second case as compression stress at the top fiber is 0.0035 and more than 0.002 plus 0.87 FYES. So that tensile strain we can have greater value. So according to that, we can create the formula. According to the first case, when we have 0.0035, which is lesser one, then we can create a stress block according to that also, na?
Yeah, I know what you are saying. See, Shivam, you are saying what if the stress in this bar is greater than this value? Strain.
Uh, Means when XU is less than XM, then there are two possible cases.
Yes.
So according to, we have created the formula according to the assumption that the stress in the steel is 0.87 Fy and it has reached that value. Means the strain जो है वो हमारा रीच कर चुका है और जो कंप्रेशन में है वो 0.0035
Nah,
है.
nah. It is not like that. Strain in the concrete, we are always assuming it to be 0.0035, and we are assuming that the strain in the steel, it should be greater than this value. It is not equal. It should be equal or greater than this value. It has not reached this value. It has
It
to.
can be said in another way also, na?
How?
मीन्स कि जो हमारा स्टील के लेवल पे जो स्ट्रेन है वो रीच कर चुका है, वो जब हमारा 0.002 है तो उस समय कंप्रेशन
Yeah.
स्ट्रेन जो है वो अभी रीच नहीं हुआ है.
Yeah, you. I know what you are saying, but the standard definition we are taking it as, we are always considering the strain in the concrete to reach 0.0035, because we want to utilize the maximum concrete strain, because concrete is a cheaper material than steel. Steel is costly, so we want to use the maximum strain in the concrete than in the steel.
Actually, I tried to calculate it up.
Yeah,
If we have taken a stress lesser than strain lesser than 0.0035, so
yeah.
we were getting a value very close to the moment as calculated from the upper assumption.
Yeah, I know what you are saying. See, according to your assumption, we can even take an entirely steel section. But what you are saying is we want to limit the capacity of our concrete section, and prior to that, we are trying to give that stress to our steel. But see, the way things are going is we want it to be in a more economized design, rather than a design which would be using more amount of steel. Yeah, you can do it. There is no harm in that, Shivam. You can do it in that manner also. But the standard way which IS 456 follows is this, and you are also required to follow this standard procedure only, because this is the safest and economic design. Conceptually
Okay,
you can do that. I'm not saying that you are wrong, you can do that, but there is some reason behind doing this. Just remember that.
that is concrete is cheaper material.
Yeah, concrete is cheaper, we want it to utilize it fully, while steel is. And apart from that, we need to use the warning of steel. If we are using less steel, then also it is good, because we will have more warning. You are getting me?
Yes, sir.
Okay, so
Yes.
okay, so that was the reason. Any other questions?
My question, another question was related to the shear reinforcement.
Okay.
If when you provide the data about that, then I can put forward my question.
So I
Or
will be coming up with questions on shear reinforcement in the next class. Would that be fine for you?
yes, sir.
Okay. So now we have finished the design
Okay,
of
sir.
doubly and singly reinforced. We have finished the calculation of ultimate moment of resistance calculation. We have seen the behavior of different types of steel, Fe250 and Fe415. We have see how to calculate the factored load and partial factor of safety for the material as well as for the load. So this all are the things we have already covered up with some problems, and in the next class I will be definitely coming up with problems on shear. So that's all about this class, and now I would be winding up with this. So thank you all. Let's meet up in the next class.